Very good morning to you all. Myself, Manu, faculty with Photogrammetry and Remote Sensing Department, IIRS Dehradun. I'll be taking the second webinar in the series on radiometric corrections and normalizations of satellite data. In the last series of this webinar, we had discussed what type of errors are there in the data, both with respect to radiometry as well as the geometry of the data. So we had dealt with what kind of common radiometric errors and geometric errors do occur in the data, what could be the causes of the same, and I had also taken a brief account of the geometric correction due to rotation of Earth for the satellite images. So coming back to the radiometric errors, as we had discussed, that due to the changes in digital numbers that needed to be recorded from the target to the sensor, there could be some changes in these values. Now, these changes could be due to systematic errors or non-systematic errors. That is what we have discussed in the last class also. Now, today, the main frame of this class will be to make you understand what could be the process chain of radiometric calibration or correction or normalization. We will be dealing with the approximate methods of radiometric corrections in the remote sensing images. I'll not be taking up the artificial correction methods of correcting for dropped lines or or line start or salt and pepper noise, etc., because we have discussed this earlier in the last part of this series. So I'll be mainly discussing with once you receive the satellite data and once you have freed the data from the bad columns or bad bands, what next you do in terms of radiometric corrections. So here, the basic processes that you will need to address will be: step number 1, you would convert the digital numbers to spectral radians. I hope you understand what is radians, because the prerequisites of this webinar requires that you have a basic understanding of remote sensing process and some terms associated with it. For the sake of just a revision of that, I'll just briefly tell you what is radian. See, we need to measure the energy coming from the target to the sensor. Now, this energy needs to be measured both in terms of space and time. Now, this energy which is reaching the sensor comes in a definite interval of time. So, we need to have information of energy per unit time. Also, it is coming from a particular area, and it is also falling onto a particular area of the sensor. So we need to have an information of energy per unit time per unit surface area. Again, the sensor, as you see that your eyes are also like sensors, some detectors, we have a field of view. We can't see in the entire sphere, right? So we have a field of view in a solid angle or an angle in 3 dimensions. We can perceive the information. Similarly, the detector on board will also have a field of view. So we need to also get the information on what is the solid angle that the information is coming from. So we need to have information of energy per unit time, per unit solid angle, per unit area, which is embedded in the form of radians. Also, every detector is sensitive to a certain bandwidth. Bandwidth as in spectral wavelength range. Okay, so we need to also have this information of energy with respect to wavelength range. So effectively it becomes energy per unit time, per unit area, per unit solid angle, per unit wavelength. Wavelength you can take as micrometers or nanometers, or whatever units of wavelength you want to take. Just a moment, I'll All right. So this is what we mean by spectral radiance. So this is the actual physically measurable quantity that goes to the sensor, right? Now this quantity, when it reaches the sensor records this information, and then it converts this information to digital numbers, right? So there is a calibration process which relates the spectral radiance with the spectral digital number values. And this calibration comes in the form of usually a linear calibration. So for a linear relationship between radiance and digital numbers, you will have a slope and an intercept. So these slope and intercept values can be taken and can be used to find the radiance from the given digital number values. Because see, the digital number values do not have any physical significance, right? To convert them into a physically measurable quantity, you need to have them in some radiometric unit. So here we have taken it as radians. So radians can be computed from the digital numbers, given that in the metadata of the file, you have the bias and the gain. Bias is essentially the intercept and gain is the slope of the straight line. All right, so for example, I'll show you how this goes for Landsat. So I'm on a web link, and so this is the formula they use for Landsat. Yeah, here. So L lambda is the spectral radiance, okay, and Q cal here is the digital number, okay, and L min lambda is the offset or the intercept. Okay, the rest of the quantity L max minus L min divided by Q cal max minus Q cal min, these quantities can be taken from the metadata of the file. Now, what are these quantities? See, Q cal min and Q cal max. These are the minimum and maximum quantized calibrated pixel values. So it's like the corresponding to the sensitivity of the detector, you will have the range of these values. Okay, for an 8-bit sensor, Q cal min here for Landsat is taken as 1 and Q cal max is taken as 255. And L max and L min will also be given by the data provider, where these are the radiances which correspond to the corresponding minimum and maximum quantized DN values. So in an effective manner, this is the minimum DN value possible using the sensor that you have taken. This is the maximum DN value. Corresponding to these minimum and maximum, you have a record of radiance, which you can call as L max and L min. Okay, this will be dependent on different spectral bands. So the prefix lambda or subscript lambda is also indicated. So usually these 4 quantities, L max, L min, Q cal max and Q cal min, these are provided in the metadata of the file. So you can use this linear relationship to convert the digital number to spectral radiance. All right, I hope that's clear. Okay. So next step, once you have converted the digital numbers to spectral radiance, the next step is the conversion of spectral radiance to apparent reflectance, or we also call it as top of atmosphere reflectance. So this is the total reflectance due to the target and the interaction with the atmosphere also coupled together, reaching the sensor. Now there is a relationship between how you can convert radiance to at sensor reflectance. There are some factors which can be used to convert this radiance to reflectance, which is a function of Sun to Earth distance will be dependent on which day of the year we are looking at. There is also only a slight difference, but still there is small variation depending on the day of the Julian day. Julian day is like 1st February is 32nd Julian day. If there are 365 days, so 31st December will be 365th Julian day. So Earth-Sun distance will be taken in terms of astronomical units. This can be easily found. We can find it from the web. That what is the Earth-Sun distance in different Julian days. Okay, so this factor can be taken provided you know at what time of the day or at what time of the year the data was captured. Then the other thing that you need to have is the information on solar zenith angle. Okay, solar elevation or solar zenith information should be there with you when the data was captured. Then the third thing that you need to know is exo-atmospheric irradiance. So, dependent on the sensor and the spectral region, the exo-atmospheric irradiance will vary. So, this information will also be given by the data providers. For example, again going back to Landsat data, you can see that the equation for radiance to top of atmosphere reflectance is provided here, where this rho is the planetary reflectance or the spectral top of atmospheric reflectance, pi is 3.14, and then L lambda is spectral radiance, which you have already computed using the digital number. D is the Earth-Sun distance, as I said, in astronomical units. And then E-Sun is the mean solar exo-atmospheric irradiance, which will be different for different bands. And theta is your solar zenith angle. So, for example, Landsat provides the exo-atmospheric irradiance for all of its bands in certain units. Okay, watts per meter square per millimeter. Okay, so you can convert it corresponding to the units that you have and then compute the reflectance. So, this way you can find out the information from the metadata of the satellite information that you have, and you can convert the digital numbers first to spectral radiance and then spectral radiance to apparent reflectance, or in other words, top of atmospheric reflectance. Now, once this is done, whatever information you have got here in terms of top of atmospheric reflectance, let me maximize the screen. Yeah. Okay. So that contains the information not only from the target itself, but also the information from the atmosphere. Because while incoming, the direct beam of the sunlight, this before hitting the target, interacts with the atmosphere first. Some amount of absorption happens, so some amount of signal is diminished, and then some amount of scattering also takes place. So there is redirection of light in different directions. Now this energy, which has gone through the atmosphere, altered in its magnitude and its direction, this reaches the target, and what does the target do? As I said in the very beginning class also, that we will be dealing with the optical remote sensing in our webinar series. So, in the optical remote sensing, we are dealing with the reflective kind of remote sensing. So, part of it will be reflected, part of it will be transmitted, and part of it will be absorbed. It is the reflected component of energy which is coming from the target to the sensor that we are interested in. Now, this diminished signal, this redirected signal, this reaches the target. The target reflects some part of it. Now, this part which is reflected again has to travel through the atmosphere. Then the atmosphere again will absorb some part of it and scatter some portion of it. and again this altered signal reaches the sensor. When this is the direct beam of light which is going to the sensor, which was partly scattered and partly absorbed, both while incoming as well as while outgoing. However, it is also possible, due to scattering of radiation within the atmosphere, some component of light which has not even seen the target also gets added up in the same direction of the light which is going from target to the sensor. So this entire information is embedded in the form of top of atmospheric reflectance. So this POA reflectance, or we call it as apparent reflectance, will not give the precise information of target reflectance. The target reflectance will be different from this apparent reflectance. So what we need to do, this step number 3, we have to correct for the atmosphere. So what we do is, we try to estimate the atmospheric effects due to the major two type of interactions, that is absorption and scattering. So we try to estimate the transmission properties, the path radiance, the spherical albedo of the atmosphere, the molecular absorption, scattering due to aerosols, etc. Okay, so we try to model all this information. More details I'll be discussing in the atmospheric correction part in the last part of, in the third class of this webinar series, that is in the next session. But today we will be focusing on the proximate methods of radiometric calibration or correction or normalization. So in step number 3, we try to estimate the effect of atmosphere. We try to model it and remove this atmospheric component from the apparent reflectance. So what we get is now the target reflectance. Okay, this step from 2 to 4, this is on this entire thing comes into atmospheric correction. Okay, so I rewind here. We are starting with the digital number values. We convert them to spectral radiance. From spectral radiance, we convert to spectral apparent reflectance. Then we may stop at this level also if we are going for qualitative remote sensing. But for the sensors which have poor signal to noise ratio, or if we are going for quantitative remote sensing, then we need to do atmospheric correction also. That is, we need to go for estimation of atmospheric effects and then remove this atmospheric component from the top of atmospheric reflectance and calculate the target reflectance at the Earth's surface. So this is the entire process chain of radiometric corrections. All right. So here, with this, as I said, that the most difficult process in the entire chain is estimation of atmospheric components. Why? Because atmosphere is dynamic. It is dynamic both in space as well as in time. And different vertical sections of the atmosphere, there also it is changing. So the estimation of atmospheric parameters at the time of acquisition of imagery is a very tedious task. Either you need to carry the atmospheric measurement instruments at the time of capture of image, or you try to model them, or you use different remote sensing products of atmosphere and then use them to retrieve the surface reflectance. So the most difficult part here is estimation of atmosphere at the time of image acquisition. So here we have two choices before us. We go for either relative or approximate methods, and second is the absolute methods. So relative and approximate methods will be the ones which we will be dealing with now, and absolute methods will be taking up in the next class. So as I said, we'll be discussing some of the commonly used approximate methods for radiometric corrections. Right? So here, the first method that I'm going to discuss is the dark object method, or it is also called dark object subtraction method, DOS. which is commonly found in several image processing softwares, and this can be automated or the different remote sensing images. Now, what we do here, see, the major assumption that we make here is that the effect of haze or the atmosphere is going to add up some information on the image. So let me make it full screen. Yeah, now fine. So, so what we assume is, as I said, that the atmosphere has an additive effect on the entire image. Although this is not a valid assumption in all cases, but it works very well for at least the hazy conditions. When the image is having some haze in the data, then you can simply go for dark object subtraction. What you do here is you pick up some pixels, those features whose surface reflectance should be negligible. Okay, for example, in visible bands, complete shadowy regions should have near zero surface reflectance if it is in a complete shadow region. Or if you have a water body in the in near infrared region, there also you assume that the surface reflectance should be near zero. And such dark pixels should have near zero surface reflectance in the corresponding bands. However, if you find that there is some amount of reflectance or some amount of digital numbers over those pixels which you assume should be having zero values or near zero values, so there you can pick up those pixels, take an average or choose the minimum value and subtract this minimum value or the average of the dark pixels from the entire image. So what assumptions did you make? You made, number one, the assumption that the effect of haze was additive in the entire image. Number two, you assumed that this effect of haze was homogeneous or was evenly distributed in the entire image. Okay, so if you are going for large swath images, like big images of remote sensing data, then you can make small subsets and then do this dark object subtraction over different subsets. Okay, so this is one of the very old and very simple methods, but it gives effective results for the cases where you find haze in the image. Okay, if you don't have complete shadowy regions or if you don't have water bodies in the data, what do you do? Which pixels or which features you should pick up? You can pick up the dense vegetation pixels in the blue and the red part of the spectrum, because in the bluish and reddish spectral range, due to pigment absorption, the spectral reflectance is assumed to be very low. Okay, so these should be behaving as dark targets in blue and red wavelength regions. So depending on which features are there in the data for those corresponding bands, you can select them, assume the reflectance or the DN values or the radiance values associated with those pixels to be coming from the haze effect of atmosphere, and then subtract this value from the entire image. This method works fairly well at the DN level also. Suppose you don't want to go for radiance and then reflectance, etc. You just want to work at the digital number levels only. If you want to have just a view of the changes in the different temporal data sets, you can work at the digital number values also. It works well at the radiance level also, and of course at the top of atmospheric reflectance levels also. So this is one of the very commonly used methods in the remote sensing images for approximate radiometric corrections due to atmosphere. All right. The other method which I picked up for you is again very simple: internal average relative reflectance. We call it as IIRR. Now what we do here is, suppose we have a radiance image. This again works on radiance also, DN also, and top of atmospheric reflectance image also. So suppose I have considered a radiance image of any particular band, and I can take the average of the entire image. Now I can divide each pixel value with this average of the entire image. And with this method also, to some extent, the effect of atmosphere is reduced. How this is reduced is because we have assumed, number one, the atmospheric effect is not additive, but it is multiplicative. So if it is multiplicative, so if you divide the actual pixel value with the average of the entire image, in a way, you remove that multiplicative factor. So the assumption that we make here is it is multiplicative effect of haze that is affecting the entire image. In actual conditions, it's not totally additive, it's not totally multiplicative, it is coupled effect. Additive also, multiplicative also, and in a very complex manner, and not in the scalar form, but in the vector form, the components are introduced. So making the life simple, we can assume either the effect of haze to be additive, or here in this case, as we've assumed it to be multiplicative, and we can work with different temporal images. Okay, the name is relative reflectance because the values will be somehow relatively normalized. This will not be reflectance actually, but it will be the relative reflectance kind of image that you'll be receiving. You will have values which can be greater than 1 also, because the average will be less than the maximum values. So wherever higher pixel values will be there, you'll be receiving values greater than 1 also, and the range will vary, right? So the major drawback is sometimes it introduces artifacts in the entire image, but it's good enough if you don't want to go for complex computation for atmospheric correction. Another one such method is flat field method. So here, for using this flat field method, you need to have in your image large, bright, and homogeneous targets. When I say homogeneous, then there should not be a very frequent change of features within a particular feature range. For example, here in this image, if you can see the cursor, I'm pointing my cursor here, you can see that this is a large, flat, bright, homogeneous patch. Okay, not very undulating at the similar elevation level, and it's having very high reflectance values also. So if you have such a target in the image, instead of dividing each pixel value with the average of the image, you can divide it with the average of this flat field. Okay, so here also again the assumption is that the effect of atmosphere was multiplicative, so it would have been removed when you have taken the ratio of the image pixel divided by the mean of this flat field. Now the values will be more in the range of 0 to roughly 1 or slightly greater than 1. Right? So this is a good method, better than IIRS if you have a flat field target in your image. All right. Another method is scene to scene normalization, which is also very, very commonly used if you are working with temporal analysis of similar spatial domain. So here, what we need to have is, number one, we need to have some pseudo-invariant objects. That is, those objects which hardly change their behavior or spectral reflectance over time. Okay, so these could be your, let's say, some pixels. If it is sand, if it is a sandy region, you can pick up some pixels from sand or very, very bright pixels, or you can take some urban features which are not going to change much over the time period. Of course, there will be slight changes in the spectral reflectance due to the presence of moisture or the alteration due to time. However, still we can consider them to be having nearly similar spectral reflectance over time. That is why we call them as pseudo-invariant or pseudo invariant features, PIF. So if you have such features in two of your images, let's say I have image number 1 taken in timestamp number 1 and the image number 2 taken in timestamp number 2. Now these two different images might have different solar illuminations, might have different haziness because of they have been captured at two different points of time, or they might have gone some changes in the features also. However, if you have some pseudo invariant features in both these images, you can plot a curve between the radiance values of image number 1 and image number 2. You can consider one of them to be master and the other of them to be slave. So with respect to one, you try to do a normalization of the other. Now, ideally, if there had been no change in the features that you have selected, those, let's say you have selected 5 features, 5 pseudo invariant features, and these are perfectly not changing with respect to time, then you would have got a straight line y is equal to x passing through the origin. However, because these are pseudo invariant, there might be some changes due to the feature changes itself, or due to solar illumination conditions, or due to different pollution effects, local pollution effects. So you will have some slight deviation from the actual slope of 1. You will have another slope which is not equal to 1. Okay, and there might be an intercept also. So you can use one of them to be master and one of them to be slave, and correct one with respect to other using the linear equation that you have got. Okay, so here the major condition that you assumed is in your images you have pseudo invariant features. This method is very commonly used for cross calibration of one sensor images with respect to other sensor images, or doing a time series analysis when you have a set of pseudo invariant features over time. Okay, so this is also called scene to scene normalization, or invariant object method, or pseudo invariant features method, or invariant object regression method. So for temporal evaluation, or for evaluation of changes which are happening temporally, you normalize one image with respect to other. It's not a correction. It's not a correction in the actual sense, but it is normalization. Normalize one image with respect to the other image. Okay, so this is another method which you can look into for your projects. Then one of the very good methods which can give you the results close to the absolute methods is the traditional approach of using the ground truth methods. So here what we need to have is, we need to have in an image, you need to have a flat field, that means some bright, homogeneous and flat target, and you need to also have a dark target. Okay, for example like this. So in this image you have a dark target and you have a bright target. Now what you need to do is, at the time of image acquisition, if you have sufficient resources, when I mean resources means you have access to this area, you know that the satellite is going to pass at, let's say, 10:30 a.m. today, and you carry your instruments. In your instruments, I mean spectroradiometer. Now what this spectroradiometer does is, it can capture the spectral reflectance of the target. So you point your instrument to the target and you will record the spectral reflectance, the target reflectance, or you can say it as in situ measurements, ground reflectance, ground truth. So you take measurements of the reflectance from the dark target. You also take the measurements of the flat object, and now you have taken a record. Now after some time you'll receive the image also. When the image comes to you, you just do the conversion of dn to radians. Okay, you convert the image to spectral radiance. That is the step number 1 of radiometric calibration that I taught you in the very beginning. So you plot a curve between the ground reflectance and the image radiance that you have received from the image for the dark targets and the bright targets. I have shown here for one point each, but actually you can take it from number of points. You'll have number of points here in the dark target. You might have taken some measurements. Okay, so you have reflectance and you have the corresponding radiance. So this ground reflectance is coming from the spectroradiometer and this image radiance is coming from the image. So what you got? You got a direct relationship between the image radiance to the ground reflectance. So for that, you needed to have dark target and bright target both, so that you don't deviate from the actual relationship, but you have the entire range of the reflectance, the entire range between the dark and the bright. So you have a direct one-to-one mapping for image radiance to ground reflectance. You only measure the ground reflectance at two regions, flat and the flat bright and then dark target. But you got the mapping for the entire image. So this way, we also call it as empirical line approach. So what we need to have is, the requirement is, you should have control panels or ad hoc control surfaces of known reflectance, okay, the dark and the white patches. And then what you do is, you linearly regress the radiance or against reflectance. You can do it with DN also, if there is a linear calibration relationship between the DN and the radiance, which is so for most of the sensors that you commonly use, Landsat, MODIS, then OceanSat, then Indian sensor, other Indian sensors also. So you have usually a linear relationship. So you can start with DN also. But for non-linear relationships, you So this method is also called empirical line approach. So you have a direct relationship between the radiance and the reflectance. So spectral reflectance directly. Now you don't get apparent reflectance. You get target reflectance. That means from step number 1, you are directly jumping to step number 4. So target reflectance is equal to gain, that is the slope of this line, into radiance plus the offset, the intercept, right? So we have discussed some approaches where I've discussed with you dark object method, where we assume that the effect of haze is additive. Another method is histogram matching method. There again, we assume that the effect of haze is additive. So what we require to have for histogram matching method is, you need to have two time scale images, let's say, again timestamp 1 and timestamp 2, one with haze and one without haze. So if suppose this is the condition, then you'll see that the histogram of the image in the hazy image will be stretched towards higher DN values. So what you do is, you try to take it back. You try to match the histogram of the hazy image with the histogram of the non-hazy image. This method can be applied on a single scene also. If you have a big homogeneous patch, let's say if you have a big agricultural region where you assume that, okay, the histogram variation should be similar at different patches of that image. But some patch has higher haziness, maybe due to local smokes, local burning somewhere, and the other patch of the image is free from that. So considering that and that portion of the image which is free from haze, you can take the histogram of that patch to be the reference and try to match the histogram of the hazy patch with respect to the histogram of the clear patch. So this way you can have different approaches of atmospheric correction. You can assume a model of your own also, to remove the component of the atmosphere or to minimize the component of the atmosphere from your images. These are all approximate methods. So for additive effector phase, I've discussed, with this assumption, I've discussed dark object abstraction and histogram matching. For multiplicative effects assumption, I've discussed two methods again, internal average relative reflectance and flat field method. For scene-to-scene based normalization, where you don't want to consider either the additive or the multiplicative effect in actual, but you can normalize one image with respect to other. You can use scene-to-scene normalization, but the problem is you should have pseudo-invariant features. If you don't have such features, for example, you can't choose vegetation, you can't choose water bodies. Water bodies, only the dark water bodies, very calm, smooth, dark water bodies can be chosen. But otherwise, soils or water bodies, these can't be used as such because these will be altered with respect to time. Okay, and then one of the very good methods is the ground truth method, the traditional approach or the empirical line. But again, you have to have the resources available with you where you can directly map your digital number or your image radiance to the ground reflectance. So with this, I thank one and all, and I'll be happy to take up some questions from your side. Maybe let's take a break again for 5 minutes and we'll be back for our interaction session. Thank you.